All right. So we said we want to learn policies that maximize some notion of reward or performance across multiple time steps, right? And so there's going to be multiple ways to do it. The first is model-free reinforcement learning, model-based reinforcement learning, and imitation learning. And we'll start by covering imitation learning, and we'll come back and study model-free RL. So we talked about imitation learning through behavior cloning. And the key idea is that we want to cast imitation learning as a supervised learning problem. So we pretend that it's a one-step prediction problem. And we just try to maximize the likelihood of experts' actions at expert states, right? And this, you can think of this as like any regression problem. You're trying to say you have a function that takes an S star and tries to predict A star with highlight. And so it's the same as mean squared error, cross entropy loss, things that try to minimize the difference between the predicted action and the optimal. So that's a simple scheme, which we talked about, just takes all the data, throws it in the replay buffer, treats it as like a standard regression problem, and then just does the work. So it's really, really simple. You don't need rewards. You don't need any extra fancy stuff. But as we discussed, the challenge with behavior cloning really is that the imitation learning setting is not the same as supervised learning setting, because you're not in the one-step case, you're in the multi-step case. And so if you make a little mistake, the little mistake compounds over many, many, many steps. Right? And so the key issue with most of these supervised learning style imitation learning methods is that the supervised learning is done over the distribution of data B. Right? You're saying on S star, on states S star, you're going to try and maximize the likelihood of expert actions A star given S star. But when you evaluate your policy, you're going to roll it out under phi, not under D. Right? So if you make little mistakes, those little mistakes get bigger and bigger and bigger as you go further and further and further. Right? And so that's the primary issue with these imitation learning methods. Right? Does that page into everyone's memory okay? Okay. So that's the issue, right? And so the general principle we talked about is that if you can have corrective labels that bring you back to the data, then you don't have this issue getting worse and worse over time. Right? So let's say the compounding error issue happens when you take a step, and the step is a little bit away from where you saw the training data. And so let's try and start up. And so you have like an initial state. This was the training data, right? You made a little bit of a mistake, you ended up here. Made a little more of a mistake, you ended up here. Made a little more of a mistake, you ended up here. You're deviating, right? Whereas if you knew that you can get corrective data so that when you get here, rather than deviating like that, you come back to the training data, right? Then you are unlikely to have these issues going further and further. And so the first type of technique we discussed to enable this corrective behavior is this idea called dagger, right? And so dagger, the loop is pretty simple. It looks something like this. So essentially the key idea is that you want to make the data distribution as similar as possible to the distribution when you run the policy forward, right? So the previous step we saw, when you run the policy forward, you might have like deviating errors. So essentially this is the data distribution and this was the policy distribution, right? So like this is the policy and this is the data, right? And you kind of want to make these the same. And so what dagger does is it says, it's like the dumbest possible thing. It says, okay, this is what the policy distribution is. Take this and add it to this. That's it, right? But the important thing is that on the states in the policies distribution, you're not going to just take the actions that the policy took. You're instead going to take the actions that an optimal demonstrator would take, right? So for instance, if I was here and I had an optimal demonstrator, the optimal demonstrator would not do this. The optimal demonstrator would come back, right? Or the optimal demonstrator would come back, right? And so the difference is you're going to roll out the policy. You're going to see, okay, it deviates, but on the deviated states, you're going to label them with a human or with an expert. And that it doesn't have to be a human, it has to be an expert. And if you label them with an expert, then you're going to take those actions where you have these accumulating errors and label them expert demonstrations, or I label them with expert actions, right? And so now you have a bigger data set that consists of these states and these states. And at these states, your actions are labeled like that. And at these states, your actions are labeled going back to the manifold of data, right? So the reason there's like a bunch of theoretical proofs that you can write about it, but the key intuition is that if you take, it's like whack-a-mole, right? It's like if you, if you are saying that, okay, you've gone out of distribution and I don't know what to do there, right? If I just add that data into the data buffer and I do tell you what to do there, then the next time you get there, that will happen. And so you're essentially widening the data distribution so you don't just like deviate into crazy stuff. So we discussed this a little bit last time, but what makes this, unreasonable? So Noah brought up a point last time, right? It's like, isn't this just data collection, right? And the important thing is that it's a little more than data collection. It's data collection, like Noah's point was, okay, if you're going to do this anyways, just collect more data. And the important thing is you're not just collecting data at arbitrary states, you're collecting data at states where the policy is likely to reach when it's making mistakes. And so you're collecting data on a very specific set of states, not just random states. And so if you compare it, it's like collecting more data versus using that data in specific states, that tends to work a lot. So that's the difference with collecting more data. But if you look at this paradigm, like what about it is like kind of unreasonable. So you train a policy from human data, easy enough. You're gonna like run that policy to get the data set, and then you're gonna ask a human to label all the states that the policy reached with optimal actions, and then you're gonna aggregate them. But what is unreasonable here?
Yeah, the human labeling might take a lot of effort.
Human labeling might take a lot of effort, but even more weird than a lot of effort, it's that you're asking the human to label the states that were reached with optimal action. So you have to do it after the fact. So imagine that you roll out your policy, you did something crazy, and now the human has to go look at the states where the robot was in, and then like tell it what to do. Rather than you're not embodying the system when it's executed, you have to go in after the fact and like provide corrections, right? Which is like kind of a weird way to do things, and it's often unintuitive. So I don't know if I had this today, but there's like this drone example that I showed last week, right? So this drone is flying around. What you have to do is you have to take pictures that the drone saw and then label whether you go that way, which is like not always easy to do for all systems. And so one, it's tedious and it can often be like hard to do after the fact. What's another issue that you might find? Like, let's just look at these 4 steps. What else might be expensive in this whole process? So aggregating is just like adding to equivalent set. So yeah, memory will grow. Yeah, but like the other problem is that you have to run your policy in the environment. So like if your policy kind of sucks, you have to like run it in the environment and get like things might be unsafe. It's expensive to like run things in the environment, right? And so that like if we can avoid running things in the environment, life will be a lot better. And so what we're going to try and do next is we're going to try and think of some ways to kind of like fix this compounding error problem. And fix the issues with tagging, right? And so the first issue is that we want to like avoid having to run the policy after the fact on like potentially crappy states. And the second thing is we want to like we want to avoid asking the human to label with these optimal. And so we're going to try and discuss 2 methods that solve these. These are less like Dagger is a very seminal method, and the 2 methods I'll discuss are more new under research topics. But they kind of do an interesting thing, right? So let's start by thinking about the first, which is I don't want to have to like keep running the policy at test time and do autonomous unsafe behavior and then relabel them. So can I do something like fix things at data collection time so I don't have to keep running the policy after? And so the idea that some folks at Berkeley introduced was very simple. It's basically like rather than trying to run the policy after the fact and keep adding that to the data set, let's do something really simple. When we're collecting data, add some noise to the process, right? So the way it's going to work is that imagine a noise-free process. You're controlling your robot, let's say, with a VR controller. And so you're going to like move your policy right through the middle. But the problem is you have no data here and here and here and here. Right? And so the data is like, there's no noise in the data. So if you make mistakes, those states are just like, if the policy makes mistakes, those states are things that the expert never showed you. So what you're going to do is really, really simple. let's say the expert told you to go here, you're gonna like add some noise to it. And so the policy is gonna go here. And then, or like the system is gonna go here. So your VR controller tells you to go here, your system goes a little bit off. So you add some noise to it. And then the human has to like correct for that noise. And so the point is that you're like forcing the system to be noisy at training time, so that the human provides not just optimal behavior, but corrective behavior, right? And so as a result, what happens is that you don't just see this narrow set of optimal states in the middle. The noise is going to drive you to states off the optimal path, right? And then the human is, when you're providing data, think about it like, an easy example is, think about you're controlling this robot, and it's like, it's not like perfectly actuated. It's like always giving you some noise or drifting, right? And so you provide like corrective labels because you're a human and you're good at doing that. And that widens the set of states that you see. And if you widen the set of states that you see, then you have less of this compounding error because you formed like a tube around the optimal things, right? So essentially, like if this was your optimal data, right? What you've done is, okay, this was what an expert would have done. And I'm going to like introduce a bit of noise, and then the human is going to correct it. Introduce a bit of noise, human is going to correct it, right? And so then you have like essentially a cube around the optimal data where the human is providing corrective behavior, right? And so you essentially have all of these now in your data set. So let's say you had compounding error, right? So you were here, made a little mistake, now you're going to end up at this state, but the human has already provided some corrective data. Right? And so if you just do this really, really simple trick of like adding some noise during training time, it like increase your success rate by like 30%. It's like very, very fast. And it's like very stupid. So if any of you are ever doing imitation learning, just like always do this. It'll always help. Almost always. I'll tell you why it doesn't help sometimes. But so they formalized it a little more. We don't have to go into the details, but basically what they're doing is a maximum likelihood approach, but they're doing it under data, which is noisy. And so they have like this like epsilon noise vector, and they're kind of like add in noise at training time. And so there's this paper from fall 2017, which tries to do this and like infer the optimal noise and things like that. But the key idea is just add some noise during training time. That's it. And why is this better than Dagger? Because you don't have to do this awkward after the fact labeling. You're doing it while collecting data. And you don't have to keep rolling out your policy after the fact. It's all done at training time. It's one and done. Right? So that's going to help a lot, right? And so they used it for bed making. So they like had this bed and they're kind of like pull up the sheets and do things like that. And it's a fairly long horizon task. So things start drifting a lot if you don't put these corrective labels in. And they found that it's super effective to just add some noise during data collection. Especially with interfaces like VR, like they're very easy to correct, right? So even if you want a demo, you should come to our lab. We have some demos where you have some noise to the system. Cool. Does that make sense? Simple idea, right? Very effective. But it's not always a good idea. So when is it not a good idea? Like when might it be a bad idea to add noise? Yeah. Yeah, if you're exactly, if you're in a safety critical system or if you're in a high precision system, sometimes you cannot add noise to the system like that. And so you need to be able to like find a different way to do it. And so the next thing we considered is one of the papers from my group, is that we're trying to like solve this issue of not having to inject noise at training time, but also trying to like avoid having a human label these optimal actions. We're trying to deal with both the issues. And so the premise is still we're trying to deal with compounding error, but we want to operate under the same assumptions as behavior. We're going to like assume that we get some optimal data, no noise, and we want to like get corrective labels without a human and without like noising the training process. Because the reason we were doing so is that we were trying to do extremely precise tasks. So we're trying to do like picking up a coin or doing like really precise insertion, and you can't have noise, like you just can't demonstrate things with that. And so so our insight was we want to generate corrective labels automatically, but without assuming a lot of stuff, right? And so how might we do this? If you guys can tell me how the paper works, just write tell you how the paper works. Like, if you were to like, so the assumptions, let's think about the problem, right? The assumptions are you're given the human data set, and you are not allowed to run things in the environment, and you are not allowed to ask a human for coordinates. And you are not allowed to add noise at random. So we really made it life hard for ourselves. So what could you do? Any ideas? No? Come on, yeah.
Like models, like the environment, or like.
Perfect. You should be an author. It's basically that, right? It's basically that. So essentially, what we're saying is that if we knew a model of the environment, then the environment model can tell you how to generate corrective labels, right? So imagine that you had deviated off the optimal path, you had reached this state, right? Like, let's say you reached this state over here. If you knew how the environment worked, right? You can say, let me find the action. So if I knew my dynamics of the environment, right? And I knew that I was at some state S, and I wanted to get back to some optimal state S star, right? I can say, like, what are the actions that I need such that when projected through the dynamics will bring me back to an optimal state? So it's saying that if I knew how the system worked, then I could go from, if I knew some S and I knew some S star, I just need to solve for what, A will bring me from S to S star. And if I knew the system dynamics, then I could do that. Right? So let's try and write this out a little more formally. So if you knew a model of the environment, right? Let's say you had like an approximate model of the environment. And what you could do is you could search for, if you're at some state S, you can search for an action A, which brings you pretty close to an optimal state. Right? So it's saying that if you were here, you can search for the action that brings you close to an optimal state. And so it basically just says you can use the model of the environment and how the environment transitions to figure out what actions bring you back. Right? The problem is I made all these restrictions on you, so you don't actually know the model of the environment, right? All you have in your problem assumptions are you have expert data and no model, right? And so what we're going to try and do, the magic sauce is we are going to like learn our dynamics model from that training data. And so we're going to say, you take this expert data and you like learn a dynamics model of how the world transitions, right? And the problem is that that dynamics model is only good on expert data, right? I trained it on expert data. Why would it be good anywhere else? And so this paradigm works well if this F is accurate. It doesn't work well if this F is inaccurate, right? And so the insight that we had is basically if you like impose a little bit of smoothness on the dynamics model, you can just like make the dynamics model not change too much, right? So you can think of like, in most systems, the world doesn't change very, very abruptly, right? So if you say the dynamics model doesn't change so much, then if it's trained on this data, then it can be kind of trusted on things in the neighborhood. And so essentially, the idea in our work was, we're gonna take the data, use it to learn a dynamics model, which is smooth, like, doesn't change too much. And then use that to design corrective labels that go back to the data. Right? And so you're still operating under the same assumptions as behavior cloning. You're not asking the human for labels. You're not putting noise in the data collection process. And so you're satisfying all the assumptions that you want. The main thing that you have to do is you have to learn an approximate model of the world. And we'll cover this in the model-based RL lecture, but for now, just think of it as like an approximate model that tells you if you're at state S with action A, what S prime would you reach, right? The motion model, the dynamics model, the same thing that we talked about. You learn that, and then you try to find things that under that model bring you back to the data. Does that make sense? Intuitively, right? And we applied it a couple of cool tasks. This one I like. The goal is to insert this little gear thingy into this thingy, and when the gear train is fully inserted, then it starts spinning. Right? So you have to be really, really precise, like millimeter precision. And so behavior cloning, you can see kind of like tends to drift off, right? So you can see behavior cloning misses it. So it like made a small mistake at the start and it kind of drifted off. And is no longer successful. But if you do this like adding of corrective labels and AGI, look at that. But point being, like, this is one particular way to do it, but the main point I want you to take away is that if you have compounding error, think about ways to stabilize your system. And think about ways to bring your system back to states that it knows what to do. Things for. And so whenever you're trying to think about imitation learning, like, don't believe everything you see on the internet. Always try to like deal with compounding error. It's gonna matter. Any questions? Yeah. It's the same system, but it's the next paper after. It's the same system. It's a paper called CCIL, which we haven't really released yet, but it's hot off the press just for CSE 478. Okay, but the main point I wanted to convey with both of these ideas was, so Dagger brings you back to the data distribution by adding more and more human labels, but it's expensive. The last paper we discussed, which is like noise in the data distribution for dark, essentially that's like changing the training time so you collect corrective data. And this paper, which is called CCIL, is trying to like synthesize that data automatically from an approximate model of the world. But all of them have the same idea, just come back to the known data. Yeah. Cool. All right. So does this solve all our issues? Can we declare success? Any intuition on why, what other issues might be? Thoughts? Relation studies? Yeah. Between the human and the robot. Yeah, definitely. Like in a lot of these systems, we're assuming that you're controlling the system in its own embodiment. And so like a lot of these correspondence issues don't happen as much because you're like directly controlling the robot. But the specific issue that I want to like highlight a little more is this idea of multimodality. Right? And so we haven't really discussed this a lot, but here's one way to think about multimodality. It's like, if you have a probability distribution, right? Like, let's say this was X and this was P of X, right? Something like this, it's a unimodal distribution, has one mode, right? But something like this is a bimodal distribution, has two modes, right? And so a Gaussian fundamentally is a unimodal distribution. And if you try to fit, if you let's say collect data from a distribution like this, try to fit a Gaussian to it, you cannot capture both modes. No matter what you do, the Gaussian cannot magically split up and capture both, right? And so the best solution trying to fit multimodal data with a Gaussian is to average the modes, right? And so the best solution, imagine if you try to fit like the best possible Gaussian, the data from here, your mean is going to be the sample mean, your variance is going to be the sample variance, it's going to end up right in the middle. And so this is usually okay, but let's see why it's not okay in imitation. Okay? So imagine you had a tree. You have a drone flying right at the tree, and sometimes you go left, sometimes you go right. Right? So it's essentially a bimodal distribution, like at this point right here, right? Like essentially half the people go left and half the people go right. But I'm trying to fit this with a Gaussian, right? Like, so a lot of policies are Gaussian, and like, last time I described mean squared error. Imagine you're trying to do mean squared error, which means you're trying to say, like, make your prediction a hat, as close as possible to the expert actions, right? But the expert actions were 50% this way and 50% this way. And if you're trying to say your predicted action is closer to the expert actions on average, then what's going to happen is that you're going to like average them. And for a tree, you're going to go straight into the tree, right? And you typically don't want to go straight into the tree. So the issue is that when you have a multimodal demonstration set and you're trying to fit it with a unimodal behavior like a Gaussian, then you approximated the wrong, right? And so that's going to lead to catastrophic behavior, and multimodal behavior is extremely common. Like you ask me to control a robot to do something and you to control a robot to do something, we do something different. Or like 10 different people who are driving are going to drive differently. And so like most sets of demonstrations are multimodal. And the problem is that a lot of times in behavior cloning, we try to use Gaussians or mean squared error are unimodal things. And unimodal things can never fit multimodal things. And so there's like a fundamental misspecification problem. And so you're just trying to fit a multimodal thing with a uniform thing. You will lead to the wrong outcome. And in certain cases, it's fine, right? If I was in free space, let's say some people went here and some people went here, and I went here in free space, it doesn't matter. But it can be really bad in certain cases. So, so that's basically the issue, right? You have this bimodal thing, best Gaussian fit, sticks you right in the middle, fix the problems. Okay, so that's the issue. Now, how can we fix it? Any ideas? So let's say, we had one Gaussian is clearly not going to fix. One Gaussian will have it fixed. What is a different probability distribution that can capture two Gaussians? Has anyone heard of a mixture of Gaussians? Okay. Maybe this question is ill-posed. But basically, you can think of a mixture of Gaussian as, imagine you have one Gaussian, which is like, P of X is a Gaussian with some mean and some variance. Right? You can have a mixture of Gaussians, which is basically like you have X given C as this, and for each of them you have a different Gaussian, and then you have a mixture of Gaussians. So while a Gaussian will look like this, right? A mixture of Gaussians will look like some combination of Gaussians, right? And so you can construct richer families of probability distributions, which are able to capture this behavior. Right? And so a lot of the research in multimodality is saying that Gaussians are insufficient, and we want to use richer families of probability distribution. So a lot of you might have heard of diffusion models, right? Diffusion models are again a richer class of probability distributions that are able to capture multimodal probabilities. And so we'll skip the details, but the important thing here is that we can use a bunch of different ways of doing it, right? So let me talk through some of the really easy ones, and then I'll leave the rest as an exercise, right? But a really easy multimodal distribution is the categorical, right? So imagine you had a discrete, like if you had no continuous actions, you just had discrete actions, right? And so you had you can almost think of it as like a probability table. Yeah. And a probability table where this is like, P of X1, this is P of X2, blah, 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 right? A probability distribution that's a table is naturally multimodal because you can have this one be 0.5 and this 0, 0, 0, and this one be 0.5. That's a valid table. And the valid table is bimodal, right? And so like discrete distributions are naturally multimodal, or they can capture multimodal things. But the problem with discrete distributions is like a robot is not discrete, right? And so a lot of this work in tree is basically how do you try to convert robot continuous spaces into discrete spaces that can capture these multimodals, right? So using the fact that a table can be multimodal, whereas the Gaussian cannot. Right. And then there's more fancy work that tries to do this with, a diffusion model. And then you get like, and let's see if I can play these, right? And so you can see that, like, for instance, with this task, some people pushed it this way, some people pushed it that way. And so this kind of shows like a diffusion model that's able to capture multiple ways of doing things. And so don't worry about it too much. It's not a probability class. The important bit is that if you have very diverse demonstrations, then you want to like rich and expressive way of capture. Kind of make sense? Intuition, at least. Okay, great. So, some cool imitation learning videos. This one that came out from 1X last week, which I thought was pretty awesome and creepy and So the important thing to note about these videos is that this really work. There's a collective of all parts of the energy. The intent of working things is not very good for the legends. Okay, so that's one. Another one that is cool is from the jumper, where they have this from image with imitation. So the very key part of the setup is that when you see you can like talk with your so it's like really a nice operation setup where they can collect a lot of data, public during this thing, and they get pretty cool autonomous behavior. The caveat again is that it's very close to the trading. It's not necessarily. So, as good skeptics of science, I would encourage you whenever you see videos like this, there's good things to take away from it. Obviously, it's like very impressive, but ask like, what is the training distribution? What is the testing distribution? Is it at 1x speed or 10x speed? Like, try to figure out like, what is the scope of generalization, right? And that's going to be important because if you had a really narrow setting, I could just like hypothetically. Okay, so that is basically my insight on imitation learning. It's really nice and easy to use. You don't need reward functions and extra infra. It sometimes be unreasonably effective, right? Like we just saw. But it naturally has the challenge of compounding errors and multimodality. We don't really know that it generalizes meaningfully yet. And it can often be really, really expensive in terms of data collection. To have a human sit and collect data, that is an expensive process. Okay. Cool. So those are the insights on imitation learning, and we should move to reinforcement learning. Any questions on imitation before we do that? You all feel like experts on imitation learning? Kind of? Okay, good. Cool. So let's move to reinforcement learning. Okay. Let's move to reinforcement learning. But we'll start by thinking about model-free reinforcement learning, right? And the reason it's model-free is because we're not trying to build an approximate model of dynamics. So in the last, if you remember the CCIL paper we talked about, we're trying to like approximate how the world works, build an approximate dynamics model. In model-free reinforcement learning, you're not going to try and do that. You're just going to try and do trial and error, right? So model-free reinforcement learning is saying, I want to interact with the world. Unlike imitation learning, we're not going to assume that you have demonstrations. You're only going to assume that you have rewards. You're only going to assume that you can interact with the world, right? So no demonstrations, access to reward, and interacting with the world. And the goal is to keep interacting with the world to maximize rewards. That's it, right? And essentially what model-free reinforcement learning is trial and error. So let's say, try a bunch of stuff, do more of the good stuff, do less of the bad stuff. That's it. That's the whole outcome, right? And we like derive the math behind it, but essentially it's as opposed to imitation learning where someone tells you what the good stuff is. In model-free reinforcement learning, you as a robot have to try a bunch of stuff and then pick out the good stuff and discard the bad stuff. That's the whole outcome. Okay, so let's try and derive it, right? So this is going to be like a little bit math heavy. So I will try and write it on my little iPad, but the goal in reinforcement learning is to maximize the sum of expected rewards, right? So we said here that if we sample the trajectory from the policy, right? So you started from S naught, we sampled A naught from phi theta of A naught given S naught. We sampled S1 from the dynamics of the environment. And then we sampled A1 from pi theta of A1 given S1. You repeat, right? You get essentially a trajectory, which is S naught, A naught, R naught, S1, A1, R1, S2, A2, R2, right? Till SE, A2. So you just like repeat the sampling process. So this is like an action sampling process. This is a dynamic sampling process. And then you repeat these until you get an entirety. Yeah. And the goal is how do we use these trajectories that we collect in the environment to figure out how to maximize reward? So the objective that we have is saying that when you sample trajectories from your policy, you want to figure out the parameters of your policy theta such that you maximize the sum of rewards. Okay, so we're going to use a little bit of shorthand here to make our life easier. R tau is going to be the sum of rewards in a trajectory, right? So let's say you have trajectory tau, R tau is going to be the sum of rewards in the trajectory. Yeah. And B theta tau is going to be the probability of a trajectory. And so the probability of a trajectory can be written as the probability of the first state times the probability of the first action times the probability of the next state times the probability of the next action, so on, right? So this P theta tau is going to be essentially shorthand for this, right? It's, you can write it as P of S naught times the product of phi theta AT given ST and P of ST plus 1 given ST and AT. So it's basically initial state multiplied by likelihood of a policy multiplied by likelihood of the dynamics. Right? And so this is the likelihood that you get a trajectory. This is the probability that you get that trajectory. Right? And this is the reward of the trajectory. And so the expected reward, the average reward, is essentially the integral of P theta tau, which is the probability of a trajectory, times the reward of the trajectory R tau, integrated over all trajectories. And that's the definition of an expectation. So if you have the expectation with respect to P of Px of Fx, by definition, this is the integral Px Fx. That's the definition of the expectation or the answer. Does that make sense? Okay with me? So what we did is we took a trajectory, right? So we're gonna, this sampling process is a shorthand for the process of, sampling the initial state and sampling the first action, then going to the next state, sampling the second action, repeat, till you get a whole trajectory. P theta tau is shorthand for the product of the probability of the initial state times the probability of the first action times the probability of the transition, repeat, right? So this is the probability of the whole trajectory. What is the likelihood you got that trajectory when you have that policy and those environment dynamics, right? And this is the reward of your trajectory. And so you can think of this as, this is saying, let's choose the parameters of a policy which try to get the highest average reward, right? So it's like, when I sample trajectories according to that policy, I want the average reward across all of those samples to be as high as possible. That's the objective. Yeah, everyone with me? Any questions? It's a little different than the math we've discussed so far. So feel free to ask me questions. Probability of a trajectory, reward of a trajectory, we're trying to increase the average reward. Okay. So that is that. And what we're going to do is we're just going to do gradient descent on this objective, right? So this probability of the trajectory depends on the policy parameters theta, right? Because they decide what actions you're going to sample. And so we're going to see this thing as a function of theta, and we're going to do gradient descent. So if ever you have an objective, right? Let's say max f of x with respect to x, you just do gradient descent to maximize that objective. You take the gradient of f, you maximize it, right? And so what we're going to do here is we're going to try to take the gradient of this thing and move the parameters in the direction of the gradient. So do gradient descent. Yeah. So, but it's important that we notice a little bit of a difference between this and normal supervised learning. Right? So in normal supervised learning, you have something like this. So you have x sampled from g of x, and you have f theta. So let's say we consider imitation learning. Okay, you sample s and a from the expert data, and then you had some loss function. Let's say the mean squared error between a and phi theta of a given s. Right, and so notice that, and then you're going to minimize this with respect to theta. Yeah, that's what the supervised learning objective looks like. And the supervised learning objective, the important thing is that notice that theta is inside the expectation. Theta determines the thing inside the expectation and not the thing that you're taking the expectation with respect to. Right, so you're saying you're taking the average here with respect to some data set that does not depend on theta. Right, so it's the thing you're taking expectation with respect to is not dependent on theta. Whereas in the policy gradient, you can see here that it's, things that are sampled, like if you look at this objective, the thing that you're taking the gradient with respect to is not the thing inside the expectation, it's the thing that you're taking the expectation with respect to, right? And so if we think of like E of some P of X, F of X, right? Like supervised learning is going to take like the theta dependence is inside the expectation. And in reinforcement learning, theta dependence is the thing you take the expectation with respect to, right? So this like the thing underneath the E is going to be the thing that is dependent on theta, not the thing inside. And like the thing inside is your reward, and the thing that is in your expectation is like your probability of generating a trajectory. And so the difference here is that we just need some extra math because we defined how to do this here. You can use this algorithm called stochastic gradient descent. Most of you know about, but it's going to be a little bit different math when you do reinforcement learning, just because you're taking the gradient with respect to this thing inside the thing that you're taking expectations with respect to. Yeah. So we'll work out exactly the math here, but the intuition here is that it's not exactly the same as supervised learning. In supervised learning, the probability distribution of the data does not depend on data. It's like the data that you collect does not depend on data. The data is the expert data, does not depend, right? Only thing that depends on data is your predictions. The difference in reinforcement learning is that the data that you collect depends on data, right? So it's like the data you collect depends on data to read some different. Yeah. Makes sense? Let's go through the math, and I think it'll become more clear, or maybe less clear. We'll see. So okay, so what we're gonna do, we have this objective. We're just gonna do gradient descent on this objective. Yeah. So let's work through the steps of gradient descent, and we'll try to understand why this is interesting. So what gradient descent means is that we're gonna try and do grad j theta. Yeah. Which means that we're going to say grad theta of the integral d theta tau r tau theta. Yeah, same shorthands as before. This is the reward of a trajectory, this probability of a trajectory. This is gradient with respect to policy parameters. Yeah. So under certain conditions, you can swap the gradient and the integral. And so you can write this as the integral of grad theta d theta tau r tau. R doesn't depend on theta, only p theta tau depends on theta. And so the gradient, you can think of R as a constant, right? So this is just going to be the gradient of the probability distribution times the reward p tau. It's an integral, right? So I've just written the gradient and I moved the gradient inside the integral. That's it. Okay, now the tricky part is that this whole thing is not easy to evaluate because you have to evaluate this integral, and the integrals are pain in the ass. So if I can somehow convert this into like an expectation, if I can convert it into an average over some probability distribution, then it becomes much easier to evaluate. Because I can evaluate, if you remember particle filtering and this Monte Carlo sampling, if you can make something a sum of samples, it's much easier than evaluating an integral. Yeah. So we're going to try and convert this into an expectation, right? This gradient, if I can make it an average or an expectation, it's much easier to compute. That's the point, right? So we're going to do a little bit of trickery to get there. Anyone have any ideas of how I can convert this into an expectation? So an expectation is always written as some like p theta tau times some like f tau. So the point is that you have to have a p theta tau, not a grad p theta tau. Right? You have to have like a probability, because then you can write this as the expectation of p theta tau f tau. Right? So whenever you have something of this form, it's an expectation. It's good. You can compute it with averages, right? So we need to convert this thingy into something that looks like this. How do I do that? Any ideas? No? Okay, this was actually kind of hard, so I'm gonna tell you. Oh, fuck. Great. Okay, so what we're gonna do is we're gonna do a really simple trick. We're gonna multiply and divide by p theta tau. Okay, so we're gonna say multiply by p theta tau, divide by p theta tau, grad theta p theta tau, r tau. Multiply and divide doesn't change anything, right? We multiply and divide. And now we're gonna try and group this thing together. Right? Actually, we're gonna try and, sorry. We are gonna try and group these things together into like something that's more practical. Yeah. So here's a little trick for you. If you have grad theta log p theta tau, right? You can write this as grad theta p theta tau divided by p theta tau by chain rule, right? So if you have log x, you take the gradient, it's going to be 1 over x. Yeah. And so what we can note here is that the gradient of log is grad theta p theta tau divided by p theta tau. And so the trick here is that we notice that this whole thing can be written as p theta tau. And then we notice that this divided by this is grad log. So you can write this as grad theta log p theta tau times r tau times p theta. Right? So here's the trick that we use, which is grad theta log p theta tau is 1 over p theta tau times grad theta p theta tau. Right? That's the definition of chain rule for the log. And so what we did is we multiplied and divide, and then we like used the fact that the chain rule kind of told us that this grad theta by p theta is the same as grad theta log p theta tau. Right? That's the trick. So now we have something that looks like p theta tau times some f, and so it's an average again. Right? So the nice thing is, if we have this expression, right, we can write this as something really nice, which is we can write this as, so our expression here is p theta tau times grad theta log p theta tau times r tau p tau. Yeah. So the steps are, we took the gradient inside, we multiplied and divided by p theta tau, and then we use the chain rule to convert that into grad theta log p theta tau. Yeah. And so now this thing you can write as an expectation. You can say this is expectation p theta tau times grad theta log p theta tau. That's the definition of an expectation. The definition of expectation fx with respect to px is integral px fx. And so what we did is we converted this expression back into an expectation. And the nice thing about an expectation is that I can compute it with averages. Right? As long as I have a way to sample from p theta tau, which is easy because it's just like taking samples in the environment, I can compute the gradient just by taking the average of grad theta log p theta tau times r tau. So everything's in a form that I can take an average of, right? And so I can compute the policy gradient. Like we'll talk about exactly how to do it second, but you can compute the policy gradient and move the parameters in the direction of the gradient, right? So gradient of that objective up there is this thing up there. This thing is easy to compute with samples because you can take samples in the environment. Right? So let's skip my messy handwriting and go to the solution. Right? And so this trick is often called the reinforced trick. The reinforced trick is to say, take the gradient inside, multiply and divide, use the chain rule, and this allows you to write the gradient in terms of something you can take the expectation. Right? And the trick with expectations is if you have an expectation of something, you can just compute it through an average of a bunch of samples. So you can say, let me sample a tau, let me compute this gradient, and let me average it across many taus. And we'll talk about this more in detail on Monday. But yeah, that's the base of policy gradient. Let me just give you a little bit of intuition. Essentially, what it's saying is that you sample trajectories from your p theta tau, then you weight the trajectories by the reward. And so high trajectories, you try to increase the likelihood, and low trajectories, you try to decrease the likelihood, right? So it's just saying that you can think of this term as increasing likelihood. Like grad theta log p theta tau means like move probability in a higher direction. You're saying move the probability in a direction which is higher for higher rewards, right? So it's saying sample a bunch of stuff for things that are higher reward, increase the likelihood, things that are lower reward, decrease the likelihood. That's what the subject is. Okay, we'll cover more on Monday. Thank you.
fighter one day.
Yeah. It's a nice trick. It's very pretty.
I like the assets.
Mhm.
The positions paid, he mentioned, I was discussing